In this video, we're going to look at Einstein's most famous equation and ultimately talk about the weirdness in atomic physics that leads us to saying something like this: 1 plus 1 is greater than 2. So, for us to start talking about this, we're going to talk about very, very small masses here. And to do this, it's more convenient for us to define a unit of mass that is more suitable for the scale of an atom. So, when measuring these things like subatomic particles, we're not going to use kilograms because that's way too large to measure the things that we're trying to measure. So instead, we're going to use something called the Unified Atomic Mass Unit. In chemistry, you maybe talked about this as an AMU. And specifically, this is defined as 1/12 of the mass of a carbon-12 atom. So if I take 1 mole of carbon atoms, it will give me about 12 grams, or 0.02012 kilograms. If I divide that by Avogadro's number, I can figure out the mass of one carbon atom is about 1.99 times 10 to the negative 26 kilograms. A really, really tiny mass. Well, the atomic mass unit is 1/12 of this. So if I take that divided by 12, I get 1.661 times 10 to the negative 27th kilograms. We're going to define this as a unified atomic mass unit. In this class, we're going to represent that as 1U. This is the same thing that you maybe used AMU in the past. 1U is equal to 1.66 times 10 to the negative 27th kilograms. Now, with this new unit, we can describe some really small things. So that's how we're identifying the unified atomic mass unit. We can take things like electrons, protons, and neutrons, find their masses in kilograms, very, very tiny, or we can define these in terms of this atomic mass unit. So you see that a proton and neutron, they're approximately 1 U, but an electron is much, much smaller than that, 0.0000549 U. Also, notice on these that there is a great deal of precision here. We've got 7 significant figures. This is the only time in this class that we're going to be using this many sig figs. Most of the time, I'm totally fine if you rounded it to 3 sig figs on a typical physics problem. But here, if we rounded proton and neutron to 3 sig figs, you would get exactly the same number for each of them, 1.01. But as you can see, they are not the same, and in this case, it is going to be very important that we can distinguish their masses from each other. So we are going to use all 7 of these sig figs to carry those decimals all the way through. So you'll see that a neutron is slightly more massive than a proton, and both of these are about 1, whereas an electron is very, very tiny in comparison. This information is given to you in the IB Physics data booklet. You'll see in the fundamental constants these rest masses of proton, electron, and neutron, as well as this unified atomic mass. They are represented here in kilograms, as we saw in the last slide, and in this atomic mass unit, U. There's also another unit here that we'll talk about later on in this video. So where this is ultimately going to take us is Einstein's famous equation of E equals mc squared. And rather than describe it myself, I'll let Einstein do the talking.
It follows from the special theory of relativity that mass and energy are both but different manifestations of the same thing. A somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is thought equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above.
All right, I absolutely love seeing a video of Einstein. You never really see a video of him, but that's him describing this famous equation of E equals mc squared, that mass and energy are just different manifestations of the same thing, and one can be converted into the other using this relatively simple relationship. So let's talk about the different things at play here, because we've seen all of them. E is representing energy, that's going to be given to us in joules. M is the mass in kilograms, and C is the speed of light, which we now know from our study of light is 3.00 times 10 to the 8th meters per second. And very important here that that's the speed of light squared. So because of that speed of light squared, that's a huge number. Speed of light already is a big number, but if you square that, it's larger still, which means that a small amount of mass gets converted into a huge amount of energy. If I want to figure out the energy equivalence of 1 gram of matter, I can plug that into this unit or this equation, making sure that I'm using kilograms in terms of my mass. So 0.001 kilograms times 3.00 times 10 to the 8th squared, I get about 9 times 10 to the 13th joules, a huge amount of energy just from 1 gram of matter. So what we're going to talk about are masses that are actually far smaller than 1 gram, but will still result in a pretty significant amount of energy. This equation is in the IB Physics data booklet, as if you need it to remember that equation that most of you have probably already heard of before. E equals mc squared. Here just represented with deltas to show that it's really talking about the change in mass, providing some change in energy. And I think it's important to remind you that you matter unless you multiply yourself times the speed of light squared, then you energy. So, one last thing before we can talk about really our main topic in this video, and that is we have a new unit for energy. We've talked about energy in terms of joules here, but we can also define energy in terms of something called the electron volt. Electron volt is related to joules. It's just joules divided by 1.60 times 10 to the negative 19th, which kind of here seems like a very random number. That is the charge of a single electron or a single proton. We call it the elementary charge, and it's typically in coulombs. If you divide joules by that quantity, you will get your energy in electron volts. So if I want to figure out the energy equivalence of 1 proton, which is this tiny amount of mass in kilograms, I can plug it into E equals mc squared. So this is the mass times speed of light squared, and I get in joules a pretty small amount, but that's to be expected because it is a very, very small mass here, much smaller than 1 gram. So we got about 1.5 times 10 to the negative 10th joules. If I want to convert that into electron volts, I'm going to divide this number by the elementary charge, 1.60 times 10 to the negative 19th, which gives me a pretty big number, 941 million electron volts, which is going to mean that often we won't actually even use electron volts because that is too small of a quantity. So instead, we can use mega electron volts, which is just a metric prefix for 1 million. So 1 mega electron volt is a million electron volts, or 10 to the 6th. So if I move that decimal place 6 times, I end up with approximately 941 mega electron volts in terms of the energy for this one single proton. Which then is going to give us one more unit, and it's probably one of the weirdest units that we'll see all year. It's a new unit for mass. So typically we've used kilograms or grams to represent mass. Well, if I rearrange this equation to solve for the mass, I get mass is equal to energy divided by the speed of light squared. Well, the speed of light is always a constant. So for this new unit of mass, I'm just going to plug in mega electron volts for my energy, but I'm going to leave this constant C. So this is kind of a weird way to look at a unit because it's kind of a combination of a unit and a constant, a symbol in there, but we're going to keep it as is and just define this unit of mass as mega electron volts per speed of light squared. And we'll represent it here in IB like this, MeV C to the minus 2. And you can actually see this showing up as another way that you can represent the mass of these electrons, protons, and neutrons. We saw earlier that the proton had an energy equivalence of about 941. That's pretty similar to what we're seeing here in the ballpark of what our mega electron volts per speed of light squared is going to be. So let's use all of this as kind of our backdrop for talking about this weird idea of a mass defect and kind of what I teased at the beginning, 1 plus 1 is greater than 2. So we're going to use as our case study here an atom of carbon-12. This atom of carbon-12 contains 6 protons, 6 neutrons, and 6 electrons. And we defined the atomic mass unit based on carbon-12. So let's say that we know if we have carbon-12 that the mass of this is exactly 12.0 forever U, because that's how U is defined, is 1/12 of this atom. So say then I want to figure out what the mass of just the nucleus is. Well, the way I'd have to do that is if this is the mass of everything, the mass of the nucleus is just this minus the electrons. Well, I'm given the mass of an electron here in that same unit, the atomic mass unit. And I know that there are 6 electrons here. So I can take that 12 atomic mass units and just subtract 6 electrons from that to end up with something that's very close to 12, but not quite. We got 11.996706 atomic mass units. Again, this is the only time that we'll ever use this many decimals in a physics problem, because this level of precision actually matters because our differences are so small here. So this is what I am predicting my nucleus mass is going to be. Well, there's another way to figure out the nucleus mass. If I know the number of protons and neutrons and I know the mass of each, I can try to build up and say, all right, I know that there's 6 protons and 6 neutrons. The total mass of this nucleus should just be 6 times the mass of a proton, 1.007276, added to 6 times the mass of a neutron, 1.008665. Combining those gives me 12.095646 atomic mass units. You might remember that that is different than what we saw in the last slide. We now have something that we call a mass defect. Calculating it one way, by adding up the parts, we got a number just over 12. Calculating another way, by taking the whole and subtracting the electrons, we got a different value for our mass of a nucleus here. Which one of these is right? Well, turns out kind of both, depending on what it is that you're looking for. The nucleus by itself, we measure to be this, but we would expect it to be this, which is giving us this feeling of 1 plus 1, adding these parts, is larger than the thing itself. This is what we call a mass defect. If I take the difference between these two different ways of measuring it, I get 0.098946 atomic mass units. That is the mass defect that is here. So I'm trying to build up the nucleus, but the resulting mass of the overall is smaller than the mass of the individual parts that I started with. So where did this mass go? Well, Einstein would tell you that it went to energy. That this mass got converted in some form into a form of energy. And we call this the binding energy of our atom. The binding energy can really be seen in 2 different ways. It's a reversible thing. The binding energy is the energy required to separate all the nucleons. So say you have a nucleus together and you're trying to pull these neutrons and protons apart from each other to make them separate again. It would take energy to do that because you have to overcome the strong nuclear force. The other possibility is this is the energy that's released when a nucleus is formed. So when you create that nucleus, it is at a more stable state and produces some energy in the process. So that is what we're seeing in this case, that individually we had all of these neutrons and protons. They form a nucleus that has a smaller mass, but then because of that smaller mass also produces some energy through E equals mc squared. So we can take that binding or that mass defect that we found, 0.098946 atomic mass units, and we can convert this into energy. Now there's a variety of different ways that we can do this. We could first convert this into kilograms and then use E equals mc squared to find an energy in joules, or we can use this weird unit as kind of a shortcut. That we know that 1 atomic mass unit given to us in the data booklet is equal to 931.5 mega electron volts per speed of light squared. So I can use that like a conversion factor here. That 1 atomic mass unit is equal to this 931.5. U cancels out, and we're left with 92.1682 mega electron volts per speed of light squared. That, as we remember, is not a unit of energy. I want to find energy here. That is just a unit of mass. But it is very easy to convert that unit into a unit of energy if we plug it into E equals mc squared. If we do this, you'll see why we kept this c in the first place. That plugging this in for our mass, but keeping c squared in there, we're not going to plug in 3.0 times 10 to the 8th, because this c to the minus 2 cancels out with this c squared. That those are the same thing, just inverse of each other, which means that we've got nothing left. Our energy is in mega electron volts, 92.17 mega electron volts. So all of this was just kind of a fancy way of just getting rid of that c squared, or c to the minus 2 rather, to turn this mass into an energy. The final step is you can take this binding energy that we've calculated. Remember, we started with figuring out how the mass was different between the parts and the whole, turning that mass defect into energy. Now we can take that energy and look at it comparatively with the size of the atom. I see that this nucleus has a certain number of nucleons in it. Nucleon is just a fancy term for anything that's in the nucleus, which means protons and neutrons together. There's 6 of each, which means my total number of nucleons is 12, which is typically going to be seen here as your mass number, because that's the number of protons plus the number of neutrons. Which means if I want to find the binding energy per nucleon, and my overall binding energy was 92.2, my binding energy per nucleon is just that divided by 12. Sorry that I'm rounding slightly differently here, but 92.2 or 92.16 divided by 12 gives me a binding energy per nucleon of about 7.68 mega electron volts for every 1 nucleon of this carbon atom. All right, that was a lot of steps. So I want to show you all of these steps one more time in its own slide here, so that you see it all in one place. We're going to do this next example with a sample, a nuclide of iodine 127. 127 is the atomic mass of this nuclide of iodine. If you look at the periodic table, find that iodine is number 53 on the table. That means it has an atomic number of 53 or 53 protons. So with that, my first step is going to be to start building up what the mass of the parts is going to be compared to the mass of the whole. The nucleus mass that I can find on a table, it's been measured to be about 126.87544 atomic mass units. To find a mass defect, I need to figure out how that compares to the mass of the parts. Well, there's 53 protons. A proton has a mass of 1.007276, so I multiply those together. Next, I can find the number of neutrons by taking the difference between the mass number and number of protons. I get 74 on the other side. So 74 of these neutrons, 1.008665, I get a total mass of these parts showing up at 128.026838 overall. This will always give you a larger number than your nucleus mass overall, because the mass of the parts is always bigger than the mass of the whole. 1 plus 1 is greater than 2. So here, if I take the difference between the nucleus mass provided to me and this mass of the parts that I calculated, I find that my mass defect here is 1.15140, and that's in atomic mass units. Ultimately, I want to take this mass defect and calculate the binding energy per nucleon. So my next step is I want to convert this mass into an energy. E equals mc squared. To do this, I want to start by changing the mass from U into this weird MeV c to the minus 2. I do that with this conversion factor of 931.5 mega electron volt c to the minus 2 over 1U, and find that this mass can also be described this way, 1072.53. Now, if I want to convert that to just energy instead of mass, I plug that in to E equals mc squared. This is kind of an unnecessary step once you know what this does, but plugging in the mass here allows you to cancel out that c to the minus 2 and convert this directly into an energy. This is my energy in mega electron volts for the entire nuclide of iodine. But that's not what I'm trying to find. I'm trying to find the binding energy per nucleon. Number of nucleons is the number of protons plus neutrons, which is the same as the mass number 127. So I take this value and I divide it by 127, which will give me a final answer of 8.45 mega electron volts per nucleon. You can do this many times here. There are 30 different examples on this slide, and all of these, this information is enough to give you the binding energy per nucleon for each of these different elements. So what we're going to be doing in just a little bit is taking each of these, calculating the binding energy per nucleon, and then graphing them on a graph of mass number versus binding energy per nucleon. And that's going to tell us some really important things about the stability states of different nuclides that we can find, and then what that's ultimately going to give us when we get into fission and fusion and energy states for those different atoms. So as a reminder, your task from these slides in this video is you should be able to calculate a mass defect, turn that into energy using equals mc squared, and then find that energy per nucleon for any of these atoms.